This video is about the polar form of complex numbers. So up until now, we've seen complex numbers written in the form z equals a plus bi. And this is called the rectangular or Cartesian form of the complex number. The reason it's called these is because of the way that we locate it on the Argand diagram. So let's take, for example, z equals to 3 plus 4i. Well, up until now, we could have written 3 plus 4i in the form 3, 4 as a point, and then located it on the Argand diagram by going 3 places on the real axis and 4 places on the imaginary axis, or in the imaginary direction. So you can see that it's almost like I've created this rectangle on my Argand diagram. That's why it's called rectangular form. It's called Cartesian form because this xy plane or Argand plane that we're dealing with was invented by a French mathematician called René Descartes. And you might have heard of one of his most famous philosophical ideas. He's the guy that said, "I think, therefore I am," or in Latin, cogito ergo sum. Anyway, any xy coordinate plane or Argand plane is based on his idea of being able to locate things using coordinates or Cartesian points. So that's the method that we've been using up until now to visually represent complex numbers. But now we're going to look at another form of representing complex numbers visually, or locating them visually, which is called polar form. So while Cartesian form is one set of directions, if you like, to get to the point, so starting at the origin, go out the certain number of points or spaces in the real direction, and then go up a certain number of spaces in the imaginary direction, polar form instead locates a point in terms of its modulus, which we've seen before, and also something called its argument. And I've drawn these in here. The modulus is called r, and the argument is called theta. And the argument is just the angle that the modulus of the complex number makes with the positive side of the real axis. So again, that's kind of harking back a little bit to trigonometry that we saw earlier on our course. So if I want to write my complex number in polar form, I have to work out these two things. We know the modulus, which we're now calling r, is calculated as the square root of a squared plus b squared. So let's apply that now to our z, in this case, our 3 plus 4i. And we see that the modulus in this case is 5. The angle we call the argument, so that's our theta in this case, and we're going to use a bit of trig to figure out the size of theta. So I'm going to drop a line from the point to the real axis, and this creates a right angle triangle, of which I know the sides, 3 and 4, and so I can use tan to calculate theta. So in this case, tan theta equals 4 over 3, and so theta is going to be tan inverse 4 over 3, which is 53.13 degrees. So now I have my two pieces of information. Mod z is 5 and arg z is 53.13. Don't forget, mod z is just your r and arg z is just your theta, your angle. And when we're creating the polar form, then we've got a particular structure for it, which is z equals r cos theta plus I sine theta. So once I know what my r is, my modulus, mod z, and I know what my theta is, which is my angle, arg z, I can just fill them in to have the complex number in polar form. So in this case, that's going to be 5 times cos 53.13 plus I sine 53.13. It's pretty easy to reverse the process and go back from polar form to Cartesian form. We just have to use our calculator and simply type in the real portion and the imaginary portion. So to get this line here, what I've done is just said 5 cos 53.13, that's my real part. And then separately, I've got 5 times I sine 53.13, which I've written like this with the I at the end, because this part here that I've boxed off in yellow is the bit that you can type into the calculator. So you can see here when I type in 5 cos 53.13, I get 3.00007146. And the reason it isn't exactly the 3 is because earlier on I rounded off my angle when I was calculating using tan inverse. So just to point that out. A lot of the time we will have calculations involving radians, and then they'll come out nice and exact for us. Often we also encounter angles like 30, 45 and 60. which again will give us nice round answers. But just be aware, it's possible to end up with decimal places in polar form, just like everywhere else. It's important to remember, just like in other topics where trigonometry is involved, that you have your calculator in the correct format. So if you want to operate with degrees, make sure it's in degrees mode, and if you want to work with radians, make sure that it's in radians mode. So now let's look at a couple more examples where we change between polar form and Cartesian form. So let's start off here with z equals minus 2 plus root 2i. So this is currently in Cartesian form and I want to change it to polar form. So the first thing I'm going to do is write this complex number as a point, and then I'm going to represent it on the Argand diagram. So z equals minus 2 root 2 as a point. And here's my Argand diagram. You'll notice I'm not being too fussy about the scale of my Argand diagram. This is really only a sketch. I'm not trying to accurately position root 2 or anything like that on the imaginary scale. I just want to have an idea of how the complex number looks on a diagram. So there's my z. And now I want to figure out its modulus, or, and its argument theta. Again, notice the way that I've drawn theta in here. It's the angle created with the positive sense of the real axis. So I'm coming from the right hand side here and I'm drawing the arrow back as far as the modulus to create the angle. So I'll calculate the modulus first. So r is equal to square root of minus 2 squared plus root 2 squared, which comes out as root 6. And now I want to calculate my angle theta. And I'm going to be a little bit indirect about how I get theta this time. I'm going to put down my ruler again and drop a line from my complex number down to the real axis. But you can see that the triangle that I create this time does not actually include theta. Instead, it includes this angle here. So what I'm going to have to do is calculate the size of this angle and then subtract it from 180 to get the size of theta. And for the purposes of this, I'm going to call this angle alpha. So again, looking at my triangle that I've created, it's got sides of 2 and root 2. Notice that I've written in 2 here as it's the absolute value of minus 2, so it's the distance across the bottom of this triangle. And so now I can write down tan of alpha, which is opposite over adjacent, or root 2 over 2. And in this case, that comes out as 35.26. But again, just be aware that's alpha that I found, this angle here in the triangle. But really what I want for polar form is the angle created with the positive sense of the real axis out as far as the modulus. So to find this, it's just 180 take away that alpha. And in this case, that comes out as 144.74, which makes sense because my complex number is in the second quadrant, so I'd expect it to be between 90 and 180. Notice the similarity here with 180 take the angle to the rule that we saw in trigonometry, where when you're calculating an angle in the second quadrant, it's 180 minus the reference angle. So those rules will still apply. If we have a complex number in the third quadrant, we'll be using 180 plus our alpha angle. If we have a complex number in the fourth quadrant, we'll be using 360 minus alpha, the angle in our triangle. And so then finally, I want to put all this information into my polar form. And don't forget the rule for this is z equals r cos theta plus I sine theta. So it's simply a question at this point of substituting in r and theta. So let's just stop for a second and think about what this polar form is actually telling me. It's basically a slightly different set of directions, if you like, to my complex number's location on the Argand diagram. So like Cartesian form, it's kind of like I'm starting at the origin. In the case of polar form, I imagine myself starting at the origin, but looking out along the positive real axis. So my argument, my theta 144.74, is telling me to make a turn anti-clockwise of 144.74 degrees, and then to draw a line of length, the modulus, which in this case is root 6, from the origin out at that angle. And that locates my z. So it's a form of directions that involves a turn and a distance to get to the complex number. So here's our second example then. Z equals to 1/2 minus root 3 over 2i. We want to express this in polar form. So at this stage now, pause the video and see how far through this you can get. Don't forget the steps will be, first of all, write Z as a point, represent Z on an argand diagram, calculate its modulus, calculate its argument, and then put it into the polar form format. So I've written it as a point. So this complex number is at half minus root 3 over 2. And again, because I'm looking for polar form, I have to think about my modulus and my argument, or in theta. Notice again here that my theta, my angle, is going the whole way around from the positive side of the real axis all the way around anti-clockwise until it hits the modulus. So it's always a good idea to draw that modulus in before you draw in the argument. Calculating the modulus now, square root of a half squared plus minus root 3 over 2 squared. And that comes out as 1. And now I need to calculate the argument. Well, again, like before, I'm going to draw a line from the complex number to the real axis. You can see again, this creates a right angle triangle. I can calculate the angle shaded here in red, which I'm going to call alpha, by using tan of alpha, as I know the opposite and adjacent of the triangle. This clearly simplifies to root 3. And now I'll use tan inverse to find alpha. And this comes out as 60 degrees. When I want to calculate theta then, you can see that I'm just 60 degrees short of a full 360 rotation. So it's 360 degrees minus alpha. You may on occasion be asked to write this in radians. So take a moment to see, can you convert this into radians yourself, and then unpause the video and see if you were correct. So in radians, this would be 5 pi over 3. We do see radians quite frequently in polar form, so it's important to be familiar with them. Okay, so now to take all that information and put it together to make my polar form. So again, my rule for polar form is Z equals R cos theta plus I sin theta. So Z can be written as 1 cos 60 plus I sin 60 if I want to work in degrees. Oops, I have to go back and correct myself there. Sorry about that. That should be 300, not 60. If I want to write it in radians, I can write it as 1 cos 5 pi over 3 plus I sin 5 pi over 3. And there is actually a further way of writing this as well. So by convention, usually in trigonometry, we tend to rotate in the anti-clockwise direction. But it is also possible to rotate in the clockwise direction. And if you do this, you use the minus form of the angle. So for example, I could say that I'm going to rotate clockwise by 60 degrees, in which case I'm dealing with minus 60. So it is also possible to write your polar form as 1 cos minus 60 plus I sin minus 60. And really, it's just a matter of preference here, whether you want to do your anti-clockwise and keep your angle positive, or go clockwise and make the angle negative. Both are correct. And very finally, one last possible way of representing this guy, you could say Z equals 1 cos minus pi over 3 plus I sin minus pi over 3. Of course, minus 60 and minus pi over 3 are equivalent, so it's just the same as the previous representation, except using radians. You only really tend to see this negative angle business if you're in the third or fourth quadrant, most commonly the fourth quadrant. It's not something we usually spot or notice when we're dealing with the first or second quadrant in questions. And don't feel that you need to put a huge emphasis on negative angles. You need to be aware of them and know how to use them, but it's perfectly fine to work with the positive version also.